So around F net equals 0, the slope here will tell you if it's difficult to increase the spacing between the atom or it's easy to increase the space between the atom. So the slope is very important. So the slope around F net equals 0, it's a good way to tell us whether it's possible or it's easy to do that or not. And then we say we can correlate this with the modulus of elasticity, right? So because we know that the modulus of elasticity, E, okay, we can correlate it with the dF over dr, which is the slope around F net equals 0. We say that there is a certain relation between the two. dF is representing the slope around F net equals 0. E is representing the slope that we see from outside for stress-strain curve, right? So if this is the stress-strain curve, okay, and this is the linear relation, but then it gets curvy by here. So at this region here, this region, we call it the elastic region, right? This is the elastic region. And then we said the slope at this region, this slope is E. We said if this slope is more steeper, that means it's difficult to elastically deform the material. And it's difficult to elastically deform the material because it's difficult to push the two atoms away from each other. So then the relation between E and dF over dr is what?
Directly.
Do you think they are inversely related while they are proportionally related?
Proportionally.
Proportionally related, right? If it's difficult, if you need more force to push two atoms away from each other, you need more force, then externally, when you look at the stress-strain curve, E will be having higher value. That means more, has larger value for the slope, right? So expecting E to be larger. Okay, great. And we said the reason why the material behaving in a certain way, because if you look at the energy versus interatomic spacing, we said at a certain point, E will be minimum, right? And they are, this is at E minimum, let's call it E naught, okay? Which is also corresponding to the bonding energy. And that is corresponding to a certain value at the x-axis, right? That value is the R naught, which is the equilibrium interatomic spacing. If you, coming from outside, would like to push the two atoms away from each other, you push them away from each other, you need to apply a force because the material will resist such action. If you want to apply external force, then you're going to increase the energy of the system. You will take it from this point, okay, to a new point with higher energy. And the material does not prefer to increase its energy. So as a result of this, the material, once you remove the external forces, the material will do its best to get back to the original position, because the original position will have the minimum energy. Okay, so this is explaining why when you elastically deform a material, when you elastically deform a material, okay? When you elastically deform a material by stretching the bond between the atom, once you remove that load, the material will prefer to go back to its original dimension, because that will lower the energy of the system. Okay, great. Now, what else we need to know about this? In order for the material to get back to its original dimension, okay, it needs to use some energy. Okay. What do I mean by this? Is that as you are deforming the material in the elastic region, for example, as you're deforming the material is absorbing energy, is storing energy inside the material. And once you remove your hand, once you remove that external forces, the material will use the stored energy in order to get back to its original dimension. And part of that energy also will be released as heat from outside. So if you take a sample, a material, okay, a certain material, and then you elastically deform it, and then you leave it, okay? As you are elastically deformed, when you apply the force, the material is storing energy. Once you remove your hand, okay, the material will use the stored energy in order to get back to its original dimension, and also that stored energy will be released as heat. So when you touch the surface, you'll feel some heat. You'll feel it more warmer. Okay. Okay, great. Now, what we want to do, we want to quantify the amount of energy that can be stored in the material during the elastic deformation. And to do so, we need first to border the elastic region. Because at the end of the day, I want to know, for aluminum, for example, how much the aluminum is absorbing energy during the elastic deformation. So I need to border the elastic region, okay? Where is it? Where it's gonna end? And to do so, as you can see here, it's a linear relation, and then it starts to become more curvy. So we need to identify what is the maximum value where the plastic deformation gonna start, elastic deformation gonna end. And as you can see, it's a linear relation. And once this line starts to deviate from linearity, we can say that's the point where the elastic deformation ends. Now, it's very difficult task and not an easy task. Let me tell you why. If you come here, what do you see? You see the elastic region, okay, as a portion. This is a portion of the stress strain curve, where in the y-axis you have the stress, you have the strain. You see that P is called the proportional limit. It's called the proportional limit. Is representing the point at which the curve starts to deviate from linearity. So here, the stress strain curve is not linearly related anymore. This, as you can see, it's gradually transitioning from the elastic region to the plastic region. It's very difficult to identify exactly where this, the linear relation ends. So what the material scientists agree to do is to come up with a convention, a protocol that will be followed in order to determine where is the point at which the plastic deformation is going to start. And that point, it turned out to be 0.002. Determine that point. We will be using 0.002 in the x-axis. Let's take this value, 0.002 strain. And then we're going to draw a parallel line to the elastic region until we hit the curve. Once we hit the curve, we're going to go to the y-axis to read a certain value. That value, okay, it's telling you where is the beginning of the plastic region. Okay, so that value, we call it the yield stress. It's called the yield stress. Yield, okay, sigma y. In other words, if you are in a certain, okay, if there is a certain application, and you want to deform a material in a way that it will permanently be deformed, so that the deformation will stay in the material after you release the load, that means you have to apply stresses. Do you think it's higher than sigma y or lower than sigma y? Pause for 3 seconds or 4 seconds, try to think about this, okay? Let me ask the question again. If you want to permanently deform a material, do you think you need to apply stresses that higher than sigma y or lower than sigma y? Yeah, think about it.
دكتور بس قبل السؤال الآن احنا قلنا ان P هي نقطة نهاية اللاستيك صحيح؟
Right.
والبارallel لاين هو بداية البلاستيك.
Yeah. So
اللي بينهم من P إلى البارallel لاين ايش الستيت هذه؟ إذا احنا انتهينا من اللاستيك في نقطة البي وبدأنا من البلاستيك من البارallel لاين القابل بينهم عبارة عن which state?
Okay. So this is P is representing the onset of plastic deformation, البداية, where the plastic deformation gonna start. Okay, so the plastic deformation microscopically it's gonna start at P, but we cannot determine this point easily because the transitioning here it's happening gradually. So you need to zoom in more and more, and maybe it's a bit difficult to determine this point. Okay, so it turned out it's okay to consider 0.002, and then you hit the curve to determine a value that it's higher than P, but it's okay to consider this value as the beginning of the plastic deformation. Okay, plastic deformation will start before that. Okay, will start before this value.
Doctor.
Yes.
Now, if we said so, and we do some operation with, if we did this in a material, and we assume that the delta y or yield stress is there, it will have a permanent deformation.
Right.
So we are not in the safe zone.
Right. But the difference is not that much. The difference is between, here we are zooming in. So the difference between P and we're going to find sigma y is not that much. Okay? This is why they agreed on this convention, because so instead of saying 0.005 or 0.006, they found that 0.002 will give you a value that in many cases, okay, in many cases, or let's say in most cases, will give you a value that is really where the plastic deformation can start. So your question is a very good question, but the difference here is not that much. But maybe because here it's zooming in, but here we are zooming in just to tell you sigma y is not exactly where the plastic deformation is starting. It started a little bit before it, but that point is very difficult to determine. Okay, it's very difficult to determine. And now, in real application, if you want to apply, you want to be in the plastic region, you have to apply, you think, higher value or lower value?
Higher, it should be higher.
Higher value.
It should be higher value, okay? And if you want to stay in the elastic region, then you have to apply lower value than this. Even you will not apply something that is very close to sigma y because you want to be conservative, right? This is why you have to apply lower value. And typically when they do designing to the material, to answer the Walid question, typically they have something called safety, it's called, I forgot the name. There is safety component. What? Safety factor. Safety factor. So safety factor, where they make sure the material in that application, it will not pass or will be in not expected or unexpected scenarios. Okay, so they're expecting the material, even if you exceed the set maximum value in that application, it will not go into unexpected behavior. Okay. For example, when you ride an elevator, they say the maximum value, let's say 200 kilograms. You think if let's say 3 people with a weight equal to 200 kilograms ride that elevator, the elevator will go down? No. This is a factor of safety. That maybe in reality, the material will start to deform at 350 kilograms or maybe 300 kilograms. But for safety, they say 200 kilograms. Okay. But these 2 points are not far from each other. Okay. But now, some material will not demonstrate such gradual transitioning. Some material will have, all of a sudden, you will find yourself in what's called upper yield and then lower yield, and then you continue the deformation. Like in steel, okay? Some of the steels, they have this kind of transitioning between the elastic and the plastic, okay? It's not a gradual, changing, transitioning. Okay, so what we do, well, this kind of material first demonstrates something called upper yield point and then lower yield point. So what we need to do in order to determine sigma y, we take the average of the lower yield point. See, because it's fluctuating here, up and down, up and down, up and down. So we take the average of this region, and the average yield will tell us the sigma y. Again, so the yield stress is the stress at which the plastic deformation starts. If I have material A, okay, and this is a question to you, material A and material B. You think if material A has sigma y, here's sigma y. If sigma y of A is larger than sigma y of B, you think which one is difficult to plastically deform?
A.
Why?
Because we need to apply more force in order to deform it.
Right. So we need to apply higher stresses in order to get into the plastic region. So we can classify material according to what's called the yield strength. Yield strength. So yield strength, it's telling you how much the material will resist the plastic deformation, the starting of plastic deformation. Okay? Okay, so sigma y. And we can say sigma y is representing the end of the elastic region, right? So that means corresponding to sigma y in the x-axis, we will have epsilon y, which is at this stress, this is gonna be the epsilon y, right? And we said during the elastic deformation, the material is absorbing some heat and storing that heat in the material. And to calculate that, we can take the integration under the curve, right? And that integration of this curve will tell you how much energy the material is absorbing during the elastic deformation. And since this looks like, we can assume this is it has a triangular shape. So for me, in order to calculate the amount of energy, I can do the integration. The integration is the area under the curve. So that means this can equals to half. Can you help me?
Half, I think. Sigma
Half strain multiplied by stress.
Which strain?
The epsilon y.
Epsilon y, right? Times the
yield stress.
The yield stress. Oh, that's great. So
Doctor, this will give us energy or heat, yani?
This will, heat is energy, right? So this will give you the amount of energy that's being stored inside the material during the elastic deformation. What the material gonna do with this energy? Well, it will store it. Once you remove the external load, it will get back to its original dimension by using the stored energy. So the stored energy will do two things. Number one, it will help the material to get back to its original dimension. Number two, it will be dissipated as heat. It will be released as heat from outside. That you're gonna feel it from outside. Right. Then half epsilon y sigma y. Okay. Epsilon y also from the Hooke's law, stress equals to modulus of elasticity times the strain. So that means we can write epsilon y in terms of, we can say epsilon y equals to sigma y over modulus of elasticity, right? So if you put this value, okay, if you write epsilon y in terms of sigma and E, then what we can do, we can write it in this way. So half, right, square times E. This is giving you what's called the
over E, doctor.
Modulus of resilience. Over E, sorry. So let me delete this. That will help you to calculate what's called the modulus of resilience. Modulus of resilience. So modulus resilience is how much the material is absorbing energy during the elastic deformation. To quantify this, we're gonna do the integration, okay, of this curve in the elastic region from the beginning until the end. We can approximate this by assuming we are dealing with a triangular shape, okay? Then we can say half of the base times the height. That will allow us to come up with this equation that we can use it in order to calculate the amount of the energy absorbed. Okay. Then sigma y is a very important value, the yield strength. Okay, now what else we can talk about when we talk about, so now we're done with the elastic region, And then if we apply sigma y, okay, stress that equals to sigma y, or higher the sigma y, now you're in the plastic region. What we need to know about the plastic region? So what we need to know about the plastic region is the following. First of all, we need to know whether during the plastic deformation, the material will demonstrate the same way of deformation, or we can classify the regions under the plastic deformation. So what I would like you to do, now I would like you to look at this curve. And I want to tell you that, make it simple for you, this is representing the elastic region because you have a linear relation between the stress and strain. But then once you get into the plastic region, my question to you, can we divide this region into sub-regions? Do you see any differences here between how the material is going to look like during the plastic deformation?
Yes.
Okay, can you elaborate more?
You can see the sides of the shape of this metal is decreasing or shrinking.
Right. So if you focus here at this region, you'll find that the deformation is uniform. That means at this point and at this point, the deformation is uniform. So the volume here at 1 equals to the volume at 2. That means the deformation is uniform. However, if you pass a certain point, M, now the deformation here is not uniform. We call this region, we can divide the plastic region, okay? So we can say this is 0.002, right? This is the 0.002. We're gonna draw a parallel line to the elastic region until we hit the curve. Okay, once you hit the curve, this is sigma y, which is the yield strength, right? And then after this, the plastic deformation will start, right? And we just say that we can classify this into 2 regions, one where the plastic deformation will have a uniform deformation, deformation, and another region where the deformation, the plastic deformation is not uniform. Okay? So we need to identify this point at which the deformation starts to become non-uniform. So this point, we call it the nicking point. The nicking point, because as you can see, after this point, as the cross-sectional area, okay, will start to form a shape of a neck. Okay, it's called a nicking point. Ultimately, after this point, the fracture will happen. So this always happens in a quick way. So in many engineering applications, we don't want to pass M if we want to be in the plastic region. So we want to focus more into this region for the plastic deformation. From the yielding point up to what's called M, and M is representing something called the tensile strength. It's called the tensile strength. Tensile strength. So tensile strength is the maximum value at the stress strain curve at which the nicking will start, and nicking means the plastic deformation will become non-uniform. And before this point, the plastic deformation is uniform. Okay?
Is it because the overload or overheated of the material that it can't withstand the load that it's upon it?
Okay. So what's happening, this is a very good question. So what's happening here now during the plastic deformation, it's different than what's happening during the elastic deformation if we consider the atomistic behavior or the behavior or the motion of the atoms or the behavior of the atoms during each region. During the elastic deformation, we are only stretching the bond. And if you remember in the previous class when I asked you, can you correlate this with the stretching the bond? Some of you said, well, we're gonna apply a load that is not enough to break the bonds between atoms. It will only stretch the bond, right? So that means, this is why when you release the load, the material is gonna get back to its original dimension. But once you pass this point, sigma y, now the reason why you have permanent deformation, because now you will start to, please pay attention to this. Now you will start to break the bonds and create new bonds. So we're gonna break the bonds and move atoms and form new bonds. Again, if you apply stress that equal to sigma y or higher, now you are breaking the bonds, moving the atoms, and creating new bonds. Okay? So this is why whatever deformation you see, it's permanent because you're changing the structure of the material, changing it. Okay, the position of the atom, comparing between before and after. And because you're breaking and forming bonds, okay, this can be controllable until a certain point. After a certain point, there will be no balance between the extension that you see in the longitudinal direction and the lateral dimension, and that's going to result in nicking. Okay? Now, very importantly, and now we're going to appreciate why we spend the first 6 weeks talking about the structure of the material, because we talked about something called, one type of defect, it's called dislocation. And I would like to tell you that anything that you see here at the or the reason why we are seeing plastic deformation, it's because of the dislocation. Let me elaborate more. If you apply a stress that equal to sigma y or higher, you start to move the dislocation from its position to another position. And that concept is known as slipping. Okay, this phenomenon is called slipping. So this dislocation starts to slip from one position to another. And that slip will only occur at certain planes and certain directions where you have more closed packed planes and closed packed directions. So the reason why we talked about a full chapter about defect, because here today we want to tell you we are having permanent deformation for the material because the dislocation, which is one type of defect, it starts to slip inside the material in certain planes and in certain directions. Okay? Great. Now, what else? When we talk about plastic deformation, we can say some materials are easy to plastically deform and some materials are difficult to plastically deform. Right? If we only consider what's happening in the x-axis, how much we can go further in the x-axis before the material break, then this is called ductility. Okay? Ductility. المرونة. In other words, if you can apply a stress and that stress can take the material more into the x-axis, that means the material is more ductile. If it cannot go more into the x-axis, rather it has it's showing small amount of deformation, then the material has less ductility. So my question to you, under tensile strength, you think the glass will be, the behavior of the glass can be represented by the red arrow or the blue arrow. Think about it. Let's give it 3 seconds. Okay, so let's hear some answers.
Blue.
Blue.
The blue one, because you expect the glass will not demonstrate much in terms of plastic deformation. It will break, right? So once you get into the plastic deformation region, okay, it might show a little bit of deformation, but it will all of a sudden it will break because it's less ductile, okay? And we have another word for this called brittle, okay? So for the material that does not show plastic deformation or a small amount of plastic deformation, only is showing small amount of plastic deformation, we call it brittle. Let's compare between the two. If you have a brittle material or you have a ductile material. Let's look at this plot over here. Let me delete everything. Okay. Let's go here. Okay. So you can see here the ductile material, the material can demonstrate more deformation, and that more deformation being illustrated by more strain in the x-axis. So the material can go from A to C prime. It's called ductile material. Brittle material will show small amount of deformation. So that's why it can go only from A to C. Okay. Now we can quantify the amount of, or how much the material is ductile by using either the elongation percentage, which is how much we see changes happening in the length. So L final minus L initial over L initial times 100, that will give you the elongation percentage, right? If the material is demonstrating more elongation percentage, I mean, material is ductile, right? And if it's showing less elongation, that means it's less. It has less ductility. Go ahead, please. تفضل يا. Do you hear me? Hello? 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 شباب انتوا معايا؟ So again, I think some of you had a question, right? Do you have any questions?
لا بس قطع عندنا دكتور.
Okay.
ما سمعناك.
Hopefully now is good. Okay. So we can quantify the amount of ductility. We can say material is ductile by quantifying the elongation percentage. L final minus L initial over L initial. And also we can do that by quantifying the reduction in the area, because you know, as we're extending the material in a certain direction during the tensile strength, a tensile test, it will extend it in a certain, in the longitudinal direction, for example. There will be reduction in the area. To quantify this reduction, we're going to say A initial minus A final over A initial. That's going to give you the reduction in the area. طيب. The more reduction, the more is the material is ductile. The more elongation, the more the material is ductile. Now, most of the brittle material, okay, will not demonstrate that much in terms of the plastic deformation. This is why, okay, for brittle material, okay, they will only show up to fracture around 5%, only 5%, okay? So the strain is around maximum, or typically less than 5%. Okay, great. So now we can know something about ductility. So we can call a material stiff if it has, if it's resisting the elastic deformation. We can call it resilient if it's absorbed more energy during the elastic deformation. We can call it ductile material if it can deform more during the plastic deformation, right? We can call it brittle if it's deforming less during the plastic deformation.
دكتور عفوا ايش الفرق بين stiff وبريتل؟ شوية ضعت لنا.
Stiff is only related to the elastic region. Right? It's only related to the elastic region, and it's related to the modulus of elasticity. If modulus of elasticity has higher value, it's difficult to elastically deform the material. Okay? Let me remind you again.
تمام يعطيك العافية.
Sigma equals to E times epsilon Hooke's law, only valid, please. This is only valid in the elastic region. I'm gonna say it again, because I'm sure some of you will, Allah musta'an, will have this mistake in the exam. This equation is only valid for the linear relation in the stress strain curve, which is corresponding to the elastic region. So if you go to the plastic region, so this is the elastic, then you go to the plastic, okay? This equation, the Hooke's law, only valid in the elastic region, okay? This cannot be used here during for the plastic region. Got it? إجابة واضحة? Is it clear? Is it clear?
واضح. Yes.
Okay, alhamdulillah. Okay, wonderful. My question to you now, if we were able to quantify so we just quantified the amount of energy that's being absorbed during the elastic deformation, and we used what's called resilience to describe the amount of energy being absorbed during the elastic deformation. Do you think if we quantify the amount of energy from the beginning all the way up to the fraction, do you think that's something important? Do you think that's also going to give us some idea about how much energy the material is absorbing?
معلش دكتور ممكن بس تعيد السؤال؟
طيب. Now, we said, and it's important to know how much the material is absorbing energy during the elastic, right? Do you think it's also important to know how much the material is absorbing energy during the plastic deformation?
Maybe it will use it to create new bonds.
Okay, great. What else?
To know the maximum energy the material can absorb before fracture.
Okay, great, wonderful. So if we want to know how much the material is absorbing energy, and how, in order to have this kind of plastic deformation, we need also to calculate that energy, because that energy will tell us how easy or how difficult also the material to be plastically deformed. So this is why I will introduce to you another material property, which is called the toughness. Toughness is related to how much energy we are absorbing, okay, during the plastic deformation. So I don't see a plot here. Delete this one again. Let me go back here. Okay, for example, if you have, let's say you got this curve, stress strain curve, okay. if I do the integration for this curve from the beginning all the way up to the fracture point, I do the integration of this curve. So I'm going to measure the area under this curve. Right? That will allow me to measure what's called the toughness. Right? If this area is larger, that means the material is more tougher, right? We call it tough material. So it needs more stresses, right, in order to be plastically deformed. So toughness is a material property that is telling you how much the material is resisting the fracture. How much you need to do stresses in order to take the material from its original dimension until you break it. Okay, it's called toughness. Okay, great. So let's give a look to at the some of the values. Okay, some of the values very quick before we end this class. Very quick. You see here, this is called the yield strength. It's called tensile strength, ductility. Do you expect the value of the tensile strength to be higher than the yield, or the yield to be higher than the tensile? Yellow. What do you think?
Tensile is higher.
Tensile is higher.
Because tensile is the maximum point in the engineering stress strain curve. Is the maximum point, right? So this one way, when you have a question, you want to calculate tensile strength, you want to make sure that whatever value you come up with, it has to be higher than the yield strength. Now, the question to you, what is the difference between yield strength and tensile strength? And let's end with this. What do you think? What are the differences?
The yield strength is the boundary between the elastic and the plastic, and the tensile is the
point at which
nicking will be.
Okay. And nicking is representing the border between what and what?
Uniform and non-uniform plastic deformation.
Plastic deformation. So we'll stop here and we'll continue, inshallah, in next lecture.